Good morning. My name is Ripan Kundu. Currently, I am a final year PhD student at the University of Missouri, Columbia. Today, I'll be presenting our accepted paper. The title of our paper is Job Breaking Anonymity in Excel through a Novel and Cost-Effective Chain of Privacy Attacks and Differential Privacy-Based Defenses. So let's get started. So here is my outline for today's presentation. Uh, So motivation, as we know that extended reality application has gained immense popularity in various application domains such as disaster management, military training, tourism and hospitality, education, and many more. Then what is new? So it's basically an AI application in XR. As we know that nowadays different AI models are transforming XR across these multiple domains by enhancing interactivity, personalization, and realism. Access system, as you know, that access often collect different modalities such as eye tracking, head tracking, and physiological signals, which are increasingly leveraged through the advanced AI technique to enable different utilities tasks, for example, cybersecurity prediction tasks. Furthermore, to accelerate this development, different XR vendors such as Meta or Google frequently release publicly available dataset, which allow research and developer to design a more efficient AI-enabled XR application to enhance user immersive experiences. So what is the problem then? The problem is security and privacy for this AI application in XR. As you know, that AI-driven access system which is connected to networks or cloud services are vulnerable to unauthorized access, which can lead to manipulation of XR content or user environment. So that's potentially causing the harm of the XR user. For example, an attack could compromise the XR user data security and privacy. Furthermore, as the AI application XR often rely on the personal data, which also raise the significant privacy concern as adversaries can exploit this data and these models to infer personal information. So what is privacy risk in XR? As we know that privacy is the protection of an individual personal information. Furthermore, as we also know that eye tracking data contain a lot of user sensitive informations. So, and these data are often collected using similar protocols and may involve overlapping participant pools. So adversaries can exploit this sensitive biometric information and behavioral features to infer the demographic attributes such as age, gender, behavior, and health conditions. Such information, if leaked, could be misused for targeting advertisement, insurance, and discrimination. Also, as we know that de-identifying or anonymization of data does not guarantee privacy. So, and furthermore, these risks are more pronounced when multiple datasets from the same vendor are reused. So what did in the previous work in the access privacy? So prior works actually look at different kind of privacy threats such as re-identification attacks, where attacker aim to link a certain data to another data set to cross re-identify another user. Do some sort of membership influence attack where they try to reveal if user data was used to do AI model training or not. While prior research primarily examined MIA to like privacy of the AI model and RDA for dataset level, these are performing separately as individual attacks. However, as launching this attack as an individual attack is not practical, which require access to the raw XR data, training distribution, and AI model parameters, and also that incurs more attack cost. To mitigate this kind of attack, prior work also applied different privacy mechanisms such as Gaussian, exponential differential privacy, Kalido-based DP, so basically applied in the silence map or in the sample levels to protect against these kind of attacks. The problem, they are limited to the data level privacy. The question is raised, what about the privacy of the AI models in XR systems? So that's our contribution, that we first present the first comprehensive study of the chain of privacy attacks against the AIX applications. We show that adversary can launch such attacks with a high success rate in a cost-effective way by combining membership influence attack with attribute influence attack, and then perform RDA to re-identify the real XR user without access to the raw XR data, training distribution, or even model parameters. We also evaluate our proposed method in a realistic AI access setting by adopting deep learning-based cybersecurity detection as a representative AI access applications. We also propose two epsilon DP-enable privacy-preserving mechanism to mitigate against these attacks while maintaining the model utility as well. So we furthermore we validate our proposed method using two open source data cybersecurity dataset and also a new cybersecurity dataset constructed through a user study. So this is our proposed approach. So we first, which contains three phases. So first we develop two DL models, attention-based long short-term memory and transformer, and then we apply our proposed chain of privacy attacks, and then to mitigate this attack, we apply epsilon DP based 2 privacy mechanism to defend against this attack, basically, and differentially private stochastic gradient descents and private aggregation of teacher and suball method, PATE. So our proposed attack against AX application, from the figure, you can show that the first stage of our attack is to perform MIA to confirm the user membership of the developed AI model or training data. So once we confirm the membership, the second stage is we perform the AIA to infer the sensitive attributes such as user gaze direction, head rotation, etc. And we reconstruct a new a surrogate data set. And finally, and the final stage, basically we perform the RDA to cross-link the reconstruct dataset from AIA and MIA, and with the auxiliary dataset which come from the same vendor, and therefore re-identify the real XR user data, real XR user. So we validate our proposed method in two open source dataset. One is simulation 201 dataset, one is a VR working dataset, and these both of the dataset actually coming from the same vendors. So there potentially might a high chance that they are similar participant, they have the overlapping participants. We then also evaluate our proposed method by constructing a new dataset by user study. For the user study, we have 34 participants. We're using the VR mesh simulations. We're using HTC Vive Pro headset, and our study was IRB approved. And we're using a fast motion scale 0 to 10 for the cyber sickness, for labeling the cyber sickness, and then we actually categorize in 4 cyber sickness severity classes. Uh, then we collected the pre-processed data, collected the raw data and pre-processed using the standard technique. So we collect basically the eye tracking, head tracking data shown in the table here, and this is our actually BNMS simulation. And then we actually partition the data in two subset. Yeah. So this is our results. So first we evaluate the privacy evaluation in open source dataset. So we perform first MIA in both black box and white box settings. Then we perform AIA. So and then we perform the RDA to identify the real users. So from the table, you can see that when we perform the black box and white box settings for the open source simulation 201 dataset, we have high accuracy AOC, while we slightly get a higher accuracy AOC score for the attack success rate for white box setting than the black box setting. And then we look at that when we do the sensitive attribute inference, we find that when we merge all together, we find 93%. So then what we do, we reconstruct the dataset and we cross-link the open source VR working dataset. And for that, we're using two re-identification model. One is RBFN and one is the random forest. And we get the highest accuracy for the RBFN model. And most importantly, you can see that we really identify the 4 users from that dataset. And we validate with by communicate to the vendors that have the overlapping dataset. Yeah, participants. Then we validate our proposed approach in the developed datasets. We similar like the open source data, we saw that in the white box setting, we have slightly higher accuracy, but comparable accuracy for both black box and white box setting. But when we see like that, when we average in all the feature, we said the highest highest accuracy for the eye tracking feature. As you know that eye tracking contain a lot of user sensitive attributes. And then when you cross link with this one subset with another subset, we really identify the 9 users. So and in this case, RBFN is performing better. So then we do the privacy to trade-off evaluation and cost analysis using under the chop attack. We see that when the no privacy mechanism we have a high RDA, re-identification rate. But when we apply our privacy mechanism, we get reduced in 97 to 13%. And we see like there is a 9 participant in the developed data set. There is no participant. And similarly, the open source data set, we have no participant. We also do the cost analysis where we show that basically when we perform MI without MI do AIA for reconstruct the dataset, that incur higher cost in terms of time, and we also analyze the cost in dollars. So we show like when we perform without MIA, so we see like it's a higher attack for higher time required for both of the datasets, and it's also cost for higher cost for both of the yeah, for that all. Also, like when we apply our DP based pattern method, we see like when you have a high privacy, we actually get better accuracy utility. So we our proposed chop attack against AX will to identify XR user without access to the raw data, training, distribution, and model parameters. Our proposed privacy mechanism protect user privacy against chop attacks while maintaining high utility. In the future, we plan to deploy the proposed method on actual XR headset, conduct a user study, and report the results. Yeah, here is a reference. And thank you for Army Research Laboratory DEPCOM for funding our projects. And I am happy to take any questions.